Okay, here we go. So the key for solving pattern problems and identifying the patterns is recognizing the common rule. And here are typical classifications that you will see in patterns from middle school competitions. Growing patterns have a sequence of elements that increase or decrease systematically when viewed as a recursive pattern. And you can see this, and doesn't have to necessarily be with numbers. For example, you could do circles that get progressively bigger. That's also a growing pattern. Sequence patterns are patterns of an ordered set of numbers or mathematical entities. And you could see them later too. For example, it could be 1, 2, -3, 4, 5, -6, where the absolute value of those numbers increases just like counting normally, but then every third number is negative. Oops. And a special type of sequence pattern is a repeating pattern. Repeating patterns can be generalized by recognizing pattern families that look different but have the same core. For example, you could see when sometimes fractions, when you divide them, it makes a non-terminating decimal. It'll continue 1 to 1 to 1 to, and so on. So it repeats, but the digits, it'll be in smaller digit places, so on. And finally, a geometric pattern is a pattern that has repeating shapes such as dots, lines, triangles, circles, rectangles, and polygons. Such as, consider the geometric pattern dot dot circle dot dot circle dot dot circle. As you can see, this is also a repeating pattern, and therefore for patterns, these types of patterns don't describe what patterns are just or must be. It's not like every pattern fits dryly into one of these categories. They're just adjectives to describe them, like many fall in multiple of these classifications, and some unusual patterns may not really fit into any of these classifications. So there are useful formulas for numerical growing sequences. And the common types are arithmetic sequences and geometric sequences. If any two consecutive terms in a sequence, A1, A2, A3, all the way to AN, and maybe so on, have the same difference, the sequence is an arithmetic sequence. For example, 3, 5, 7, 9, 11, and so on. It has a common difference of 2. You add 2 each time. And the difference, as I just called it, is called the common difference, which is conventionally denoted as D, meaning usually denoted as D. And the common difference, by definition, is AN plus 1 minus AN. And that holds for all the terms in the sequence. The nth term, hence, can be expressed as an equals a1 plus d times n minus 1, because from a1 to an, each time you plus d, and so forth. And actually, you notice you plus it n minus 1 times, get from 1 to a1 to an. So that's why it's a1 plus d times n minus 1. And there's also a general formula for writing an in terms of an and the common difference. Basically, to get from am to an, you plus d n minus m times. And this actually works if n is equal to m, or even if n minus m is negative. The sum of the first n terms in the sequence is expressed as Sn. For example, S12 means the sum of the first 12 terms. And for the sum of the first n terms in a sequence, it's also known as series, which you'll often hear arithmetic series and geometric series, those vocabulary. And here are formulas for the sum of n terms in an arithmetic sequence. To get from a1 and then adding all the way to an, there's a shortcut. Instead of adding them one by one, take this formula. So you'll combine terms together. The first and last is a1 plus an. Then the second with the second to last. The third with third to last. Notice that they all equal the same sum, since each time you add the here and you subtract the there. And then that's basically adding a1 plus an a certain number of times. And you can see it's clearly n over 2 times when n is even. And actually this also works when n is odd. Let's say n is equal to 2k plus 1. Then combining these, we'll first combine them k times of a1 plus an. And then there's a middle term here. To find the value of that, well, you first notice that some of the terms right next to am, which is am minus 1 and am plus 1, that's also equal to a1 plus an. And then if there were 2 am's added together, then that'll also equal a1 plus an, since you plus d and minus d. So that means that am is just equal to a1 plus an over 2. So therefore, the sum for n is odd is going to be a1 plus an, and then times the full product of k plus 1 over 2. And as you can see, k plus 1 over 2 is equal to n over 2.
Wait, what is k?
K is just a variable to indicate must be an integer for any odd number n. So we say n is equal to 2k plus 1, for instance. If n is 5, an odd number, then that'll be 2 times 2 plus 1. So then in this case, k is equal to 2.
What does n over 2 stand for?
Oh, n over 2, let's basically divide this by 2. So then, for example, when n is equal to 2k plus 1, n over 2 will equal to k plus 1 over 2, which math.
It would be n over 2 times parentheses a1 plus an.
Yes,
Okay, thanks.
you're welcome. And also, now that we saw a proof of the formula for an arithmetic series, there's actually another formula for it that basically uses the concept of previous formula, and you substitute the formula for an in terms of a1 instead. And you could easily derive that from here. And there. Geometric sequences are also a growing numerical pattern, and they're not to be confused with geometric patterns, which we classified earlier, which involve shapes. For geometric patterns, if any two consecutive terms in a sequence have the same ratio, the sequence is called a geometric sequence. Sometimes arithmetic and geometric sequences are also known as progressions. And for example, a geometric sequence can be 1, 2, 4, 8 is common, and so on. Basically, you're timesing by 2 each time. And A1 is denoted as the first term, just like in sequences usually. I don't know why I put 2. Well, an is the general term or the nth term. For geometric sequences, you could write a1 n in terms of a1 and the common ratio, which is a1 times q to the power of n minus 1. That's straightforward to understand, just like with arithmetic sequence. Formulas for the nth term. The same ratio is called the common ratio, which I just said. It's actually usually denoted by R, but it can also be denoted by Q or something else, for example, to represent the quotient instead of a ratio. And here is the formula for geometric series. It's quite harder to prove than for the arithmetic series formula, but I could provide a walkthrough to give you some sense of how it works and why it works. So you first write it as just a sum manually. Then distribute in A. Here, and then actually this is equal to r to the power of n minus 1 over r minus 1, this part. And you can see this, right? If you multiply both sides by the denominator r minus 1, and also you could flip this part to make it start from the sum r and minus 1 all the way to 1 to make seeing how they equate easier. And then if you use the distributive property for this part, then you'll end up with r to the power of n minus 1 because many terms in the middle would cancel. Does these sequences seem clear to you guys?
Can you give another example?
For which sequence?
The geometric series.
An example?
Yeah.
Sure. We could do, let's say, the geometric sequence 3 and 9, 27, these, then adding them up. I'll let you girls try it out either by adding them manually or using the formula or also applying the concepts you've learned.
Wait, what does Q mean?
Q is another way to write the common ratio. Usually, when I wrote it, I denoted it as R, which is how we standardly do it, but sometimes they could also be represented using other variables such as Q or maybe Y or anything.
So Q is like the difference?
No, I guess they made Q from the source that I used because Q also stands for quotient, which is similar to when you times it. That's a factor, but also it's kind of a quotient if you go backwards. For example, from 9 to 3, that's divided by 3. That's a quotient. Or you could look at it as R, the ratio from 3 to 9 times 3.
So like Q means quotient?
I believe so. Does anyone want to give me any answers?
I got 39.
Yes, that's correct. Which approach did you take?
I took the formula.
Nice. Yeah, you could do it either way. And that's just an example. Good job. Now, as another practice with geometric sequences, try this problem. Find the next term. Yes, Irene?
Is this pattern a geometric sequence?
Try to see for yourself. Well, actually, yes. Olivia, did you have something to say?
Oh no, I accidentally pressed the raise up hand button.
Okay, that's okay.
What kind of pattern is this number sequence?
It's a geometric pattern, which you could see too if you notice the pattern that each time you go to the next term, you times by 2/9. Okay. Looks like one of you said 4/9 in the chat. That is the correct answer. And you just multiply by 2/9, get 4/9 here. So now we're gonna move on to a Kahoot, because the Kahoot is basically the basic concepts and sequences involving numbers and other patterns. Then we're going to try some challenge problems where you think deeply. We're going to do week 6. Okay, anyone still want to join? We could, or we could start, I guess. I'll give it to 1:30 if any of you want to join before the game starts. If we're using another device, you may also consider maybe doing it on the computer using for Zoom, which may be quicker. You could just get into another tab and then go to the Zoom screen after to look at the problems. Cool names. By the way, who's Rao 5W? I just
That's me. I'm on phone right
cool. Okay, I guess we'll start now. But if you want to join in the middle, you're more than welcome. Wait, what? Okay, I guess we'll start.
I think I keep on leaving and joining for some reason.
Oh, I'm not sure. Maybe is your internet okay?
Yeah, it's okay.
Okay. Well, I'll just start for now and hope to enjoy the game. So try them out for yourself. Okay. It looks like most of you chose the correct answer. It's basically, you see it's a repeating pattern of 6 terms. And to find the 998th term, I'll say that any term an is equal to an minus a multiple k. Therefore, a 998 is equal to AR, where R is the remainder when 998 is divided by 6. So we can quickly find the remainder. In this case, you don't have to find the quotient. Which is 2. So A998 is equal to A2, which as you could see here, that equals to 1. Okay. For this problem, it's similar to the last problem. We find the length of repetition here. Competition's count is 12 letters long. And then basically you'll find the remainder when 496 is divided by 12, which in this case is 4. So basically, we're just finding A4, which in this case is P. Okay. So maybe you could consider solving first for the first 2 terms after A1. For example, A2 would be 2 times 5 minus 5, which is equal to 5. And then A3 is represented as 2A2 minus 5, which if you do is actually also equal to 5. And then perhaps soon you've examined the pattern, but then because since the previous term is always 5, be 2 times the previous term, which is 5 minus 5, always, which is still 5. Therefore, the pattern is just a repetition of 5s. Therefore, the 8th term is 5. Okay, this problem combines what we learned in week 2. I'll just talk about it briefly when I describe repeating patterns. This fraction in decimal form is written as 0. A length of 3, a repetition of length of 3, since there are 3 9s in the denominator. And the repetition, as you can see, the value is 1, 2, 3 from the numerator. Since it repeats every 2 terms, just to find first the remainder, 1, 1, 2, 3, 9, 9, 9 is divided by 3. Actually, it's just 0. It's divisible by 3. Since the sum of the digits is divisible by 3. So then, though, you have to watch out, because the remainder is 0, it doesn't mean it's equal to 0's term 0, but it's a multiple of 3. And if you observe for the terms after the decimal point, every third term is 3. Therefore, the answer is 3. We're going to do a fun problem that involves observing pattern. Okay. Here, I'll show the problem again. For here, perhaps you notice that you'll start by 2 ones, then 3 ones, then 4 ones, and then you probably see that each succeeding term will have another one in the digit space. So then the 8th term, we have to watch out since it's not just 8. Just keep in mind that the first term already has 2 ones. So then the nth term will be a string of n plus 1 ones. And this is good to solve without even noticing how it works. But we could also discover perhaps you also had some sense of how it works as you were answering this question, where any number from 1 to n times 9, and then plus n plus 1 is equal to a string of n plus 1 ones. And you could actually try to solve that it holds for n is less than or equal to 9, basically 1 digit, positive integers, by distributing 9 out as 10 minus 1. And then do plus and minus 1. This would write this part here. Should be n plus. And then if you do the lots of subtraction, this will be a certain for the ones digit. That would be 10 minus n, and then the rest, if you do, they'll all come to 1. Including digit here. And then, well, perhaps there may not even be that much ones, but just giving an example. And then if you plus n plus 1, take this number, then you'll get a string from here to here. And then this will also be 1. Since first you plus n, I think this should be 0 at first, and subtract. Then after plus n, you will carry a 1 here as 10, then another plus 1, which would add a 1 to the ones digit. Then that's n plus 1 ones. Congrats. Congrats. Good job, girls. Okay, I hope that you enjoyed the Kahoot and learned a lot. Now we're going to go into some problems that involve even deeper thinking. Let's look at problem number 2. You could read it yourself and start thinking.
Are we supposed to continue the pattern?
Oh yeah, sorry, I didn't show what you're supposed to find. You're asked to find the 198th term of the sequence, beginning like 49, 44. Anyone have any ideas to solve this problem? Shout them out.
I'm trying to find the pattern.
Yeah, it's good. That's actually exactly what the problem needs. Okay.
I think I found the pattern.
All right. Do any of you have answers? It seems so.
I think after 49 and 44, there will be a pattern.
Yeah. So what we do here, we first solve for the next few terms. It would be like this.
I think it is, I think the answer is 22.
Well, let's see. 22 indeed is a term in the pattern. But if we look to find the terms, you see then it repeats again, 22 and 11, then it'll go so on, so forth. And this has a repeating sequence of 5 terms. Therefore, it has a repetition length of 5. And actually, though these 2 terms, the first 2, don't repeat. So perhaps let's call the sequence A, starting from A149 and so on. And then map it to a sequence B that starts from 22 here and goes so forth. So it's a purely repeating sequence. And then it means that B n is equal to a n plus 2 for any positive integer n. And therefore, if we're asked to find A198, that's B196. And then applying concept we learned to find terms in a repeating sequence, we'll get to find the remainder when 196 is divided by 5. Let's obviously first divide by 10, the remainder is 6, and then divide by 5. It's 1. So it actually is 22. So you were correct. Now let's try our hand at the next problem. But actually, I think because we're running out of time, we could start with 4 this time. But if you were thinking about 3 already, don't worry. Actually, I probably will include it then as a practice in a later class or as homework. 3 is fairly easy. So let's try 4. Do any of you have any ideas how to start?
I think might be just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, then plus another 1.
Correct. That's the idea. Since the terms before was 1, 2, 2, 3, 3, 3, so forth to 11, and that happens 11 times, and 12 is the next term. First, I have to find how many terms are before. Let's call it, for instance, x terms. And since n is the next term, n is x plus 1. And to find the value of x, which is equal to 1 plus all the way to 11, maybe you have noticed how to solve it quicker. Instead of adding them one by one, you could use the arithmetic series formula. Then that's 11 plus 1 times 12 over 2. Times 11 over 2, which equals 6 times 11. Therefore, x plus 1 is 67. And speaking of this problem, there's actually a special formula for the sum of the first n positive integers, which are also known as natural numbers. That's you're correct, Yo-Yo. So the special formula n for the sum of the first n natural numbers, that's n times n plus 1 over 2. Basically, since that's a special case of an arithmetic series, it's first plus last still, such as take our case with 1 to 11, and so on, second to last, as I showed. That's n plus 1, and then have you add them n over 2 times, which worked in case of both even, odd, n. Now, implementing what we just learned about arithmetic series and the special sum for 1 to n. Oops. So we're gonna take a look at problem number 5.
I think for each one it's multiplied by 3. Or
That's close.
one is multiplied by 3, and the second one is multiplied by 2.
Well, that works for the first 3 terms, but there's actually another pattern you could see for this geometric form of triangles with matches that can be directly mapped into a sense of the formula we saw in problem 4, which with 1 plus all the way to n. Can any of you figure or see it? You could directly tell.
triangles made up of an even number of. Actually, there's a pattern of the number of small triangles that is used for, like, the first one is one triangle which needs 3 matches. The second one is 3 triangles which each need 3 matches. The third one is 6 triangles that each need 3 matches.
Yeah, you could see that's correct that each triangle needs 3 matches. And you could also look at it as upright triangles only, because many may see and think about the downward than rigid triangles, which trips them up. But if you just consider triangles upright, then you could see, yes, it starts from one triangle, and then notice for the second one, you add 2 triangles at the bottom. Then for the third one, you add 3 triangles at the bottom, and so forth. For the fourth one, you'll add 4 triangles, and then so on. So I'm actually gonna let you try and finish problem 5 for homework. If you may have already solved it very quickly, then you could also just plug it into a form if you'd like this week. And also move problem 3 to homework 2, which you may have already solved. So I think today was a good class today. There was a good amount of participation, and I think that all of you enjoyed this. And thank you for attending. See you next week.
Thank you for teaching,
Thank you.
and see you next week.
You're welcome.
Thank you.
Bye.
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 Bye. Hello. Goodbye, Sophie. Have a nice time.